started now.
Then I guess I'll introduce. So I'll welcome everyone here to Slangens' wonderful first lecture here on an intro to quantum gravity. There's a quick blurb that you can see in the event discussion, but the TLDR is this man wants to talk about a very basic way of quantizing gravity, and you can see what he's going to be talking about here, but I won't spoil his entire talk. Slang, take it away, coming all the way
Thank
from this
you,
Discord
Bubs.
server.
All right, yeah. As Bubs said, I would like to just give like a very, very conservative, very old school idea of basically the very first approach that was invented to do something that people called quantum gravity. What people actually call quantum gravity depends on person to person. It differs a little bit. There are many different standards people have for it, and in this talk, I would just like to give like a very, very narrow definition of it, which is that you take the theory of general relativity and you do the same thing that you do to quantize, for example, quantum electrodynamics, and produce a quantum theory by doing the whole Hamiltonian analysis and then putting hats on operators, and then you see where that leads you. And basically, the only case where you can actually do this is where you have a nice sort of way of slicing your spacetimes. But in practice, this is already a relatively useful class because many of the standard spacetimes that are discussed in a GR course will actually be featured in this. But more of this will be coming a bit later. So the main things that I would like to emphasize in this talk are that you can actually go through with a lot of this stuff, even though a lot of people naively get the message that QG is very difficult and it's basically like, it's so complicated, and what does it even mean, and there's like how can you possibly quantize gravity? And the take home message is you can definitely. It's just difficult for a bunch of reasons that require a bit more elaboration. You kind of need to understand the setting of quantum gravity and of gravity itself first, um, and need a few like technical terminology things in order to properly start discussing what the difficult part about QG actually is. And I think the best part to do this is to do it in the most strict sense, which is this thing called the ADM formalism. So my general plan for today is to go through the first the first three parts of this set of slides that I've prepared, and just give like a general overview of the problem of what you would do in the ADM formalism, and also give a bit of the necessary technical background in a self-contained way, so that you, even if you just listen to this one talk, you still have something to take away, that like you have learned a crash course in constraint quantization, and you've also seen an example which basically has the same features as GR. So even if you've seen just this one talk, it should be fine. The general picture of QG, though, I don't think I will be able to touch on many actually quantum aspects of it. There's just too much details to discuss on the classical level already, but there's a lot to be learned from that anyway. So I think it's going to be interesting to just discuss all of the classical stuff beforehand and really see where the quantum stuff makes things more difficult. But there's a lot of research in QG even nowadays, and I hope that near the end, so in this additional talk at the end, I will be able to speak about that a little bit. So the general outline would be that I have this slide here, which is 0, and a few things of introduction. Then I would go into specifics of GR from point 4 onwards, and just studying what the physical degrees of freedom really are. The parts that probably Proxy and some other people are more interested in are like, what is the physical content? So what are the observables? What are the quantities you can actually like talk about and study in quantum gravity? And this turns out to be one of the more difficult questions and more involved practically, let's say. And I hope I can give an overview of why it's really the practical aspect of the question that matters in this. Because on the technical side, it's basically a solved question. So I would like to state right ahead that this approach is very, very old. People have been doing QG basically for as long as QFT has been around. And even if you, but by the way, even if you don't know QFT, this talk basically doesn't have anything of that. So it should be perfectly fine if you just know your QM and you know your GR a little bit. And particularly the classical mechanics side. So also a thing that needs to be stated right away. Many people think, okay, well, perturbative versus non-perturbative. Perturbative is bad, non-perturbative is good, but we cannot do non-perturbative. Yes, we can. In principle, there is no perturbations of metrics or whatsoever in this approach. But practically speaking, there will be difficulties in actually producing the quantum side of things, although it's not impossible. There's definitely scenarios in which you can do all of this fully. Also, it's very important to know that this approach highlights all of the important features of GR and quantum gravity that you need to know, but it's not an approach that works well enough so that you can actually, in the end, calculate stuff, at least all the way. You cannot just say, I write down a Hilbert space, I have some operators, I apply them, I get some number out. In some cases you can, but most of the time it's not enough. That's just not enough actual stuff there. Overall, I would say it's not necessarily that you need to have all of this non-perturbative stuff in order to talk about QG, particularly in the low energy limit of like just being on Minkowski space and having some like gravitons going about. You don't need all of this in principle. So as far as usefulness goes, I think you might lower your expectations a little bit. But even still, I think it's quite cool that this does work, and you can learn a lot about the actual degrees of freedom of GR from all of this. So one last note about literature stuff. Again, this is very old stuff. You will find most of this in the standard books, like the one by Walt, the one by Hawking. But there's also a few people like York and Bryce DeWitt, who basically dedicated their entire life's work to this. I highly recommend checking their papers out from the 60s and 70s if you're really interested in this, especially Bryce DeWitt's stuff on quantization. But most of the stuff that I will be presenting today is just like, to some extent, it's a copy from this book with the long title here, by a guy that is well known for giving very, very detailed expositions on stuff. It's very concise and maybe a bit too concise for some people. And it's very technical, but the overall subject is quite technical, sadly. I tried to minimize this in the presentation here, but I hope I can get as many people on board with this as possible. All right, so let's begin. So first of all, What is GR? We can't really speak about gravity without speaking about GR. At least for our purposes in this talk, gravity, no matter what you want to argue for, in this case, we just say gravity is GR. And what is GR? It's a theory of some metric on a four-dimensional space-time. So it's some symmetric matrix which we require is non-degenerate and positive definite and stuff. From this, usually you calculate these Christoffel symbols, which are representative of the Levi-Civita connection, which is used to define derivatives, covariant derivatives. So these are determined from the metric, and this is the standpoint that we will take here. From the metric, you can calculate a bunch of stuff. Usually you look at geodesics, you can calculate lengths via that. Then if you have multiple geodesics that span some kind of rectangle, you can also calculate areas and so forth with volumes. On the other side, the Levi-Civita connection allows you to calculate curvatures, which you can coarse grain in several ways. You can get the Ricci curvature, and you can also get the scalar curvature. But this is just the kinematics. What do I mean by that? Well, as far as you give me just a metric and the corresponding covariant derivative, that's just sort of not a dynamically evolving space-time. That's just one metric. And I need to know how this metric comes about. How this metric comes about is what we say is the dynamics. The dynamics in question, and this is really what defines GR, as opposed to just saying it's some theory of metrics, is you give me this precise action here, which is the Einstein-Hilbert action. So this is, some people say, the simplest action. You can argue about that. In principle, here we will look at the minimal version of this without cosmological constant, but nothing really changes if you add the cosmological constant. At least not essentially. Now, a thing that immediately comes up in discussions about gravity and quantization and stuff is that when you quantize stuff, you wanna think about whether you can preserve the symmetries of the system when you quantize. The classic scenario of this would be the hydrogen atom, where you know that the hydrogen atom is, it has time translation symmetry and rotation symmetry. And you want to preserve all of those symmetries when you produce a quantum system that represents the hydrogen atom. In the case of GR, there's a bit of a semantic nightmare going on between whether diffeomorphisms, so coordinate changes, or really whatever the symmetry group of GR is. So I want to make very clear what the actual symmetry group is, so that there's no confusion coming up. The first thing that people usually talk about in the context of GR is what you could call passive diffeos or coordinate reparametrizations. This is not really a symmetry because it's trivially something that leaves an action invariant if it describes something independent of coordinates. For example, Maxwell's electromagnetism is also invariant under changes of coordinates. That just depends on how you write it. But it's not really, it doesn't really like say anything about the system. So it's not really a symmetry in the usual sense. You can make this explicit by checking, okay, my action here depends not just on the metric, but also depends on the space-time manifold M that I put it on. And in principle, when I act with a passive diffeo, so with a reparametrization, I act with it on the metric, but I also act with it at the same time, in the same way, on the manifold. So this, just by basic theorems of how integrals work, basically substitution, this leaves the integral invariant. There's nothing special here. There's no content. So there's nothing really you can say there is asymmetry. But now comes the real thing. Diffeos, and by that I mean active diffeos, which only change the metric by replacing the metric with a pullback under something, this also leaves the action invariant up to a boundary term. And this is really different. This is a statement that the fields on the given spacetime can be replaced by a different set of fields, and then the action stays the same. This is what you would call a symmetry. And this is a non-trivial statement. This is not true for just any theory. This is more specific to GR, although we will see that it's also not necessarily the defining feature of GR. So overall, what is important here is that you fix a manifold M, or just something of the same form as M, and this gives you a symmetry group. So if you have a spacetime which has a certain form and a non-diffeomorphic spacetime, for example, one that is given by R times S3, and another that's given by R times the 3 torus, then these are not the same. These are not diffeomorphic, and these have different symmetry groups. So in the context of the series, we will be fixing one given M. Now, what will we do on this given M?
I believe you actually have some questions relating to
we have questions. Okay. Could we rephrase this as we can't use the Noether theorem to get a conserved quantity from the passive diffuse symmetry? I would say yes. But it's a little bit more. It's a little bit difficult to say. In principle, I think you should say that the notion of symmetry and the stuff that applies to the statement of the Noether theorem really is only the transformations of the fields, but not transformations that also involve the space-time that you're working on. So for example, if you have something which is like a particle theory, like a theory of a single particle, and you shift the particle's position by some constant, and the action of the particle stays the same, then you have changed the value of the fields, for example. But you have not changed the value of, say, the time coordinate, the time at which you evaluate the particle trajectory. So I think you have to distinguish between those two types of transformations here. If you don't, then you can find a lot of quote-unquote symmetries for basically any integral that don't really tell you anything, really. Yes, but it doesn't really matter as much, I would say. In principle, it's really just if you call those passive diffeos, so stuff where you also act on the space-time or the time coordinate, if you call that symmetries as well, because they don't change the action, then basically every action you can think of has a symmetry. And that's not really a useful notion, at the very least. And you don't really get conserved quantities from it. So yes, I would say, yeah, you can't use the Noether theorem to get a conserved quantity. Now, Justin asks, what is an example of a theory that is not invariant under passive diffeos? I feel like that would be something where you have a background potential. But even then, I'm not sure. I feel like if I feel like in that case you can also distinguish between this in the transformations that change the potential to adjust for the change in your coordinates, and the ones that don't change the potential. But in practice, you will not be looking at such theories, I think. I really think if like what people mean by passive diffuse is just changing the coordinates by which you describe the system, and something that's not invariant under that would really be something with a preferred reference frame, some preferred set of coordinates. SR I don't think would count, no. I think it would have to be something like something where diffu invariance in diffu is completely broken. I don't think so, actually. I think you can, if you properly analyze the question, then you will be able to find that SR is also invariant under passive diffuse. It's really like it's really like asking, okay, how can I take the surface of the Earth, which is just an objective thing that exists, and how can I write it down like as a manifold? And in principle, that's invariant under whatever charts you put on it. But asking for a theory of the surface of the Earth that's not invariant under passive diffuse, that would be asking, okay, how can I make a theory of the surface of the Earth that depends on which charts I put on it? I'm pretty sure you can make that. I'm pretty sure you can make that by treating the charts differently. But I don't know what such a theory would look like. It would probably just be like something you have to make by hand. So, yeah, and with regard to SR, SR is just a given solution of GR. So the only symmetries you have with respect to the solution are the transformations in diff M here that preserve the metric, which is precisely Poincaré. But that's because it's a solution. But the solution is still invariant under changing of coordinates. Now, let me go on to the main deal. So what we want to do with GR is we want to do the classical thing of slicing up the space-time along time slices and produce a Hamiltonian formalism. So we want to produce a phase space, which consists of stuff like Q and P or X and P, however you want to call the letters. And then we want to do the whole thing of replacing Poisson brackets with commutators and then produce a quantum theory from that. This, of course, doesn't work for all spacetimes. For example, if I chose M to be the 4-sphere, then it doesn't work for that. But that's not going to be a problem for us, because something in some spacetimes like this, if they are Lorentzian, so if they actually have time and not like just 4 space directions, those are less easy to make physical than the ones that we will look at. The ones that we will look at will just be something that looks like time times something that looks like space. This class is called globally hyperbolic. There's a lot of reasons from the GR literature alone, just GR, not QG, whatever you want, just from analyzing, for example, wave propagation on spacetimes in GR, that suggests that globally hyperbolic spacetimes are a very nice and useful class to study, and even restrict to. There's even statements that say, okay, as soon as you want quantum field theory on curved spacetime to make sense, you basically have to restrict to globally hyperbolic spacetimes. Now, there's many different ways you can take that. This most conservative shrug it off take is you just limit yourself to that, but I mean, come on, we can just see what we get out of that. The second is, okay, we do it, and then once we have it for this particular type, we can see if we can generalize what we have at the quantum level. Perhaps that's possible. And then the third stance is, yeah, I mean, if you check the numerical GR literature, which is what's used, for example, to predict the gravitational waves of black hole mergers, which is one of the strongest QG in quotation marks regimes you can think of. The main thing that's used there are precisely those kinds of spacetimes. You kind of have to, because in order to do numerical GR, you need to have some initial data and time evolve it to see where it goes. Yeah, a passive diffeo is literally a change of variables. It's nothing else. That's what I mean with a passive diffeo. Okay, now in order to do this, we need to have time slices. What this means in technical terms is that you take this space-time with sigma, I will call this the spatial slice, and we need to take this and actually provide a slicing. This kind of slicing is called a foliation. What this does is, in practice, that you take the space-time. I just draw these as a cylinder basically always. And you have to provide some kind of notion of at some time t, there's this slice here. This slice, because it's spatial, it will have some kind of time-like normal vector field, which you can call n here. But in addition, there is something that goes through the entire assignment of slices. Sort of the notion of time itself, which doesn't have to agree with this R here, but it can be something more general. So you will assume that you have some kind of foliation vector field, which you can then on any given slice, you can split it into the normal and some other pieces. The details here are not so important, really. What matters is that this here, this small n, is sort of the time direction on the slice, but it exists only on the slice. Whereas this t here exists throughout the space-time. And this is a way to translate between the two. So what do we have here so far? We have metrics, and we have this splitting into space and time that's provided by the vector fields n and t here, which both point to the important point in the direction of time. In general, you will be able to change those by acting with the symmetry group of GR. But in order to have a nice Hamiltonian formalism, you need to assume that the foliation is by space-like slices, which means that the vector field t is time-like. And you also kind of need to assume that the function n here is positive, which makes it so that t is future directed. There's a nomenclature for these things here. They are called the lapse and the shift. Shift should be pretty straightforward to think about. it's basically you take something that points in the normal direction to the slice, and you just shift it by a vector. The lapse you can think of comes from elapsed time. So it's a notion. It's a sort of the difference, the differential in time between dt and dn. Sort of translating between a local notion of time and a global notion of time. Both of which, however, are not really physical by all means.
You seem to have a question regarding this
Yes.
t vector.
Yes. Yeah, you don't choose the time-like curves to be tangent to, well, which normals? To the normals of which slices? You kind of have to provide the t first. You have to provide this, the foliation first, and this foliation comes with its field t. But in principle, the foliation doesn't have to have zero shift here. It doesn't have to have that at all.
Right, so t directly comes from the foliation with no additional data?
Yes. You fix the foliation first, and the foliation induces this vector field t. And changing.
And where does it come from if not the normals?
I think it's basically that you have to provide an embedding of some abstract sigma into the manifold. So like you take this abstract thing here and you embed it into M. And for each t, you get an embedding of sigma, which gives you like the slices here. And then there's some vector field from R, and that gets and this vector field del t coming from the factor R, when you push forward it into M, that gives you t here.
I see. Okay, so there is like more data, which is you have this family of embeddings rather than
yes, but that's what a foliation really means. It means you have a family of embeddings which is parameterized by time.
I see.
Yeah.
Okay. And then this is just a choice, right? Like, can you always choose it to just be a foliation that's normal to the?
You can choose it. You can use the diffeosymmetry to set the shift to 0. You can always do that. You can also use it to fix the lapse to 1. You can always do that.
I see.
That would completely fix the diffeosymmetry, actually. I'm not sure. I think it should, basically. Yeah. Essentially, the whole freedom of applying the diffeosymmetry group to a solution, you can also translate into an action of changing what foliation you're looking at. So, in a sense, you could just start from a given metric and one fixed foliation, and then just get the whole action of the diffie group just by varying the lapse and shift. So these things are very important. These are very important in the whole formalism. In a way, they parameterize the gauge freedom of GR. Now, there's a few things I need to get out of the way, because those are usually the kinds of questions that come up when you discuss this stuff. Does this not break covariance? Well, I mean, in a way it does, but actually not really. And it doesn't really like break anything fundamental. You don't need to worry about it, is the main take. So there will be some stuff in chapter 4, which we won't get to today, I think, but it will still be covered. But basically, the TLDR is it does break covariance in that the theory that we study here will have a local symmetry algebra which changes foliations around, which is also what diff-m does, but of course it has to restrict to only this. So it can only change time-like foliations into time-like foliations, and it can only change the lapse so that it's still positive. But I mean, that's kind of what you start out from. Now, what does this give us? It gives us a picture of GR where GR is really just the evolution of 3D geometries. So there are 3D spatial metrics which change their shape and volume and stuff in time. But I think anyone that has taken a GR course should now be asking themselves, what does this mean? Which time? The time where n is set to 1, or the time where n is set to something else? Or what time, really? This is one of the bigger issues in quotation marks. Now, people often say, yeah, you can't quantize GR because it's non-renormalizable. And the main caveat here is that, yes, that's true, but what is non-renormalizable is perturbative GR. So if you take GR on Minkowski space and you take linear perturbations around that background, then you get a theory which is perfectly nice. It's just that it's non-renormalizable. And if you take the full of GR as a theory on a given background on spacetime, then you will also have the same issue. It will not be what people call power counting renormalizable. But in this approach here, we will not even be doing the usual QFT thing of splitting into a free Lagrangian and an interaction. So the whole discussion needs a different terminology. Also, we will not be dealing with renormalization in the slightest, which turns out to overall be very different in quantum gravity and GR as a whole. In a sense, you can argue that diffeomorphism symmetry forces that you do not have renormalization. Instead, we will have different issues in that it's difficult to define operators which are in diffeomorphism invariant, and those will need to be regulated in a certain way, such that it actually works. So the regulating of operators so that they are finite and don't give infinite results is what really contains all of the usual renormalization stuff in QFT here. Overall, you don't need to worry about renormalization that much. Now, if you take the viewpoint that GR is just an effective theory and we shouldn't quantize it, then I don't know what to tell you really, because in principle, anything at low energies is an effective theory, if you want to say it that way. But you can still quantize it. You can still take QED, even though that's just one part of the standard model, and quantize it. And in principle, nothing stops you from it. So there's no a priori restriction that should tell you you cannot do it. Whether you should is more of an aesthetic preference, I believe. Now, can you actually make progress on QG with this? This is a bit of a cat and mouse thing because this is the first approach to QG. If you want, this is the definition of progress on QG. But it's also not really a controllable theory in its own way. There are different variations on the canonical quantization approach, which lead further than this, but we will not be dealing with them in this talk or in this series at all. Now, let's get to it. We will be doing the ADM split. So just for info, the ADM stands for Arnowitt, Dazer, and Misner, if I remember right. These are the people that came up with the whole formalism for this. This isn't canonical. I mean, it is canonical. It is definitely canonical in the sense that you do a time and space split and then you do canonical quantization. Now, because we have slices here and we have space-time metrics, we will need to distinguish between the geometry of the slice on its own, the intrinsic geometry, and the geometry as it's embedded in the space-time, so the extrinsic geometry. Now, we can split the line element generically into this form, which is called the ADM line element. Let us zoom in a little bit on this. Now, what does this contain? The time part here looks a little bit weird because it contains the shift vector, but this really is just here because it's also contained in the space parts here. The lapse here is basically how fast time is moving, so it's your G00 component. You can, for example, split the Schwarzschild metric quite easily in this form by saying, okay, I take the usual Schwarzschild coordinates, and there's this function 1 minus rs over r, and if you take the square root, that's your lapse. You just set your shift to 0, and then you can solve for this q here. This q is the main star of the show. Q is the spatial metric, and Q is precisely what will be the main configuration variable of the theory. Now, this is very similar, if you want, to fixing a split of the electromagnetic vector potential into some gauge fixed part, for example, where the Lorentz gauge holds, and some other piece which is a pure gauge contribution. So the gauge of GR, which comes from the diffeos, is encoded precisely in the lapse and shift parts of the ADM line element, which would tell you, if you reverse the statement, that Q here is the part that is not gauge. And this is precisely what we're going to work with. These spatial metrics, because they are 3 by 3 and symmetric, will have 6 degrees of freedom. So keep that in mind. We will have 6 degrees of freedom, and we will have 6 time derivatives. So in total, at each point on a given spatial slice, we will have 12 degrees of freedom per point. Now, how does canonical quantization work? It's the usual kind of story, just with funky variables. We have to first rewrite the action in a form such that you can write it as an time integral over a Lagrangian, which will result in the ADM action. Then you have to perform the usual Hamiltonian analysis. So you do a Legendre transform on the Lagrangian, and you end up with a pair of canonical variables and some Hamiltonian. And then you just kind of see what the quantum theory should look like. Like, what is the Hamiltonian? And what kind of stuff do we see at all? Now, first of all, there are some useful functions which we need to get out of the way. The first one is just what we saw already. This is the true spatial metric, which, however, here has arbitrary indices. It's not restricted to ij. And this can be used to project stuff down to the spatial slice in a moment. The second thing is what's called the extrinsic curvature. You get it by taking the normal vector to the slice, and you take its derivative, and you kind of want to take the normal components of that. And you can do that by taking this tensor here, which is defined from the spatial metric. So the spatial metric, mind you, is just where you remove the time components. Now, you can take the pullbacks of this to the slice as well, and then you will only have the ij components, or AB. I wrote it here with AB, I mean, yeah. Now, On the slice, you have a spatial metric, so you can also define again a covariant derivative with respect to it. It turns out that this is precisely the projection of the usual spacetime covariant derivative with this projector Q here that takes you from spacetime objects to spatial objects. For example, if you have now a spatial vector u, so something which has 0 time component on the slice, then its derivative with respect to this connection here is precisely the covariant derivative with respect to the space-time connection, but projected down. Okay, I'm not clear what the true metric is. Why can't we just use the GR metric that already describes space-time? The space, you mean what the true metric is for the spatial slice? Or for the canonical variables? Yeah, you can get when you know precisely, I can answer. So the most important relation in all of this intrinsic extrinsic geometry stuff is that you can express the time derivative of the spatial metric in terms of the extrinsic curvature, using this formula here, which also involves the shift and the lapse and so forth. And essentially it says that you can take if you fix, for example, the shift to be 0, then this part is gone. And if you fix the lapse to be 1, then it's all 1/2, actually, in this case. That would be nicer. Then the time derivative is precisely the extrinsic curvature. We describe precisely the geometry of the induced geometry of the slices with Q. So the slices at any given time have a geometry that's described by Q, the intrinsic geometry. Whereas the extrinsic geometry is described by the lapse, the shift, and the extrinsic curvature. Now, with these variables in mind, we know, okay, if we have something which depends on the extrinsic curvature, then we can convert it into something that depends on time derivatives of Q, and vice versa. So this is the kind of stuff you will need in a Legendre transform. Now, in these variables, you can rewrite the whole Einstein-Hilbert action up to some boundary terms which we don't care about here. This gives you the ADM action. Let us zoom in on this because this may look a bit unfamiliar. So the ADM action has, well, this is the Lagrangian, this is the time integral, this is the gravitational coupling. First of all, the Lagrangian is an integral over the spatial slice, and it's weighted by the spatial volume factor, and also by the magnitude of the lapse, which really, if you think about it more properly, should be belonging to the time factor here. It's sort of the time volume element in a sense. Now, what's the meat of the expression though? Is the Ricci scalar, so the scalar curvature of Q itself, which, okay, this part here looks a bit like the Einstein-Hilbert action itself, but for each of the slices. And then there's an additional piece which depends on extrinsic curvatures. And this involves in particular the trace of the extrinsic curvature. What's maybe important to mention is in this metric formulation, you have that both Q and K are symmetric tensors. Now, this is an interesting formulation because there's something that we know is linearly related to the velocities of the canonical variables q. And it's quadratic in that. So the whole Lagrangian is quadratic in the velocities. That's pretty nice because that's precisely where we can apply all of the canonical quantization stuff. This is, by the way, very similar to the action of a particle where you just have something that's quadratic in the velocities, and then you have something which non-linear in it. But basically, if you take this action here and you look at the equations of motion, it just gives you a free particle in whatever it is, say, in Minkowski space. We will be looking at this example later on much more. Now, we have the action. We have it expressed in the variables that are related to velocity. Now we can actually do canonical analysis. We can do the Legendre transform. So we will first start with the derivatives of the metric, because that's relatively easy. So what we find is that if we take the derivative, then we find what should be the momentum. The canonical momentum is then given by precisely the extrinsic curvature minus some part that is related to its trace. So this is something that, by using the formula above here, we can invert for the velocities. So everything works as usual. This is what's called the ADM momentum, and it's pretty, it's the momentum. It's useful, it's central to the whole formalism. Now there's something weird that should give you pause. In the action that I've given you here, there's no mention of time derivatives of the lapse or the shift. That's unusual for many actions that you probably know, because it means that there's no way to invert the momenta for the velocities. This is usually a case where people say the Legendre transform or the Hamiltonian formalism fails. But this is not actually the case. It just means you need substantially more machinery, which is very rich and gives rise to what's called constraint Hamiltonian analysis. And we will be looking at that next. No, actually, no. The m squared should not have an x squared attached. It's supposed to be the constraint that sets x dot squared equal to some constant. Is it obvious that k is linear in Q? I mean, it's linear in Q dot because there's no higher powers of it. That's really the point here. Now, okay, so the conjugate momenta vanish. This is a bit weird, but there are ways to deal with this. Now, what this leads to, when we have done all of this, so just to give you the result before we get into the nitty-gritty details, is that you get an action, which is extended. You have the usual pieces from the Hamiltonian form of the action. So velocity times momentum, velocity times momentum, velocity times momentum. And this is what you would call the kinetic part. And from this, you can read off the Poisson brackets between the canonical variables. What you also get is this Hamiltonian piece. Usually this whole thing is the Hamiltonian. Now, what it actually consists of, however, is a bit unusual, at least for many people. It's that you get a Hamiltonian, which consists of a bunch of functions, the h's and the pi's here, which are multiplied by some additional variables or functions, which act as Lagrange multipliers. So if you see this as a true action, then this means that varying by these functions here will yield that these that the constraints here vanish. And if the constraints vanish on shell, that means that the Hamiltonian vanishes on shell. Overall, in this Hamiltonian picture, we have that the Hamiltonian is 0. So this is something that people often kind of see, and they think this is failed. This is a sick theory, but it's a hallmark of coordinate and general covariance. You can write any theory in a way such that its Hamiltonian vanishes, and it's perfectly normal. It's perfectly regular. So there's nothing special going on here, apart from the fact that it's telling us that the theory we started from is written in a way such that there is no preferred notion of time evolution, which is precisely what we know about GR in the first place. Now, with this preview, I will quickly get myself something to drink, some water. It'll just be a moment. Yeah, actually, I hope I can get to the example. Okay, so Babs said that it's worth noting that you can find very introductory examples in the Lagrangian mechanics where simply reparametrizing your coordinates will net you a 0 Hamiltonian. Proc says, oh wow, really? Yes, really. I hope we will get to that because it's very elementary. It's extremely easy to do it, but it's not so easy to reverse it. That's perhaps the non-trivial part there. So you can take any system and turn it into what's called a deparametrized form, where the Hamiltonian vanishes. But there's a lot of systems which are generally covariant, which you cannot reverse it. You can take any system and parametrize it, but it's hard to deparametrize. It's hard to deparametrize. So to reverse so to take a system with 0 Hamiltonian like here and turn it into a theory where the Hamiltonian is non-zero. This is very difficult, and for GR, it's not known how to do that. At least, apart from some very exotic constructions. Now, are these parameters allowed to be time-dependent? In fact, they have to be. I mean, it just depends on what time you mean, really. Like, time is sort of the whole elephant in the room. In a parametrized theory, the usual time parameter doesn't have any meaning. Time is an illusion, literally. Whereas if you can deparametrize the system, then you have some physical notion of time. Yes, time is a social construct. And it's actually, I think the more proper way to say it is time is a physical concept relative to a given observer, or more generally relative to some notion of clock. And if you have no preferred notion of clock, then you have no preferred notion of time, so time has no meaning. So really the main way to reverse this procedure and get something which looks like more of a normal theory is you introduce an actual clock. You introduce something by which you can keep the time in a physically meaningful way. Now, let us get to the nitty-gritty. We want the tools to actually quantize such a system. How does this work? Usually, what we follow as a procedure is we take a Lagrangian, which depends on coordinates and velocities, and we turn it into a Hamiltonian. Then we take the coordinates in the Poisson bracket, and we put some hats on it and apply this recipe, which was invented by Dirac. Just by formal analogy, by the way. It's more of a formal thing, but it works. Very often, though, it's not quite enough. It fails in Maxwell theory, in quotation marks, and it also fails when restricting a particle in R3. Yeah, this is a typo. This should be particle. And the restriction I'm talking about is, for example, just restricting the particle to move on a sphere in R3. There it already fails. So there you can already not do it. Unless you change your coordinates into radial stuff, then it's different. But if you just do it in Cartesian coordinates, then it doesn't work. So somehow this recipe is very whether it works or not depends on which variables or how you parameterize your phase space, and that's not really very stable as a recipe. So how does it fail in Maxwell theory? So let's look at it. We take the vector potential and construct from it the field strength, and then we can find conjugate momenta for it. And we must again invert for the velocities. So for the spatial components, this is perfectly fine. You just get the electric field. So in Maxwell theory, the conjugate pair is the spatial components of the vector potential and the electric field. But sadly, for the time component, you have the same situation as in GR, and the conjugate momentum needs to be set to 0, and you cannot invert. So there's something that's similar between GR and Maxwell theory in this respect. And it also, mind you, tells you that that in the Hamiltonian theory, the magnetic field has a totally different status to the electric one. Now, this is what's called a first-class constraint. A naught in this formulation here turns out to not even have time derivatives of it in the Lagrangian. And if a field appears in the Lagrangian and doesn't have time derivatives, it functions as a Lagrange multiplier. So it imposes some constraint. You vary by the field A naught, and by doing some spatial partial integrations, you find out it imposes a certain thing. What does it impose in this case? Actually, in this case, it just imposes one of the Maxwell equations, the Gauss constraint. And these constraints will be the main topic of discussion for us. For example, we can do a constraining right away, just manually. We take a particle in R3 and we restrict it, for example, even here just to R2. I was very lazy there. Just by setting those two things here to 0. We, of course, have to set the third coordinate to 0, but we also have to set the momentum to 0 because otherwise it doesn't, it moves off of the surface that we fixed it on. Now, if we take the Poisson brackets of those, then this is 1. And if we quantize that with the prescription, then we get that the commutator of the two operators here should be proportional to that entity. But if we set both of the operators to 0, then their commutator should also be 0. So 1 needs to be 0, and you cannot set these operators to 0 on states at the same time. So something doesn't work here. This is what's called second-class constraints. It's when you have multiple constraints that do not Poisson commute or do not operator commute on the quantum level. And by imposing them, you change the Poisson structure of the classical theory. You change the commutation relations. So this needs to be taken into account as well. And both of these kinds of constraints appear in general, and both need to be treated in very different ways. But we will learn in this little crash course on constraint quantization how to do that. So the general setup is that you have some kind of kinematic phase space, which I call C here, and it has some Poisson bracket. And optionally, you also have something like a preferred Hamiltonian, can be anything. You don't even need it. Doesn't really matter. You also have a set of constraints. And where the constraints vanish, you have what's called the on-shell phase space with a little tilde on it. We will be using what Dirac invented for this and which plagues people to this day, the weak equality sign. It means if you have A weakly equal to B, it means that they are equal up to stuff that vanishes when the constraints vanish. Now, again, as said, we can have several scenarios. We can have first-class constraints, which are weakly commuting. So in practice, what this means is they are proportional to themselves. There's some matrix of functions, and they multiply as a matrix the same constraints. This is something that's very usual in gauge theories. And it's, for example, if you know a bit of QFT, you know the BRST formalism. This is the kind of stuff that BRST applies to. Now, there's also the second-class constraints, which, by definition, do not weakly commute, and instead weakly, so on the on-shell phase space, they are equal to some matrix of functions which do not vanish, but rather they form some invertible matrix. And in fact, they have to be invertible because if you take some constraints and you take their Poisson brackets, you take that matrix, you go on the on-shell phase space, and they are not invertible, this matrix is not invertible, then you can extract a first-class constraint from that set that you started from. And if you remove that constraint, then eventually you will end up with something where the matrix here is invertible. So these two cases here really exhaust all of the possibilities.
What about John Connor?
Wait, where did I put it? Okay. Now, there's also the mixed case. In general, you can write, okay, this should be a weakly equals sign. So there's also the case where, okay, actually, okay, forget about that. So in general, you have some constraints and their commutator will look like something like this. At least you can locally redefine stuff so that it looks like this. And just for notation, I use I and J for a general set of mixed constraints here. And A and B refer to the first class subset, and alpha and beta refer to the second class subset. So what's required, for example, in this case, is that the Poisson brackets have some matrix here at the end, and the matrix is 0 in this piece here for the first class by definition. And it's non-zero in the second class part. And I also just require, and it's also required that in this mixed setup, that the first class constraints weakly Poisson commute with the second class constraints. Now, you can ask, okay, there are these different constraints, but are they like different in what kind of stuff they impose? And yes, they are very different. A second class constraint just removes one phase space coordinate, which means that because phase spaces are always even dimensional, that you always have an even number of second class constraints. For example, in the point above, we had 2 here. But this is different for first class constraints, like the Gauss constraint here. That one removes 2 effectively. But we will get to the point of why it does that. The main in the TLDR is that it removes 1 degree of freedom directly, and then you have to perform a gauge fixing, which removes another coordinate. You could, for example, also say that you take P3 here as a first class constraint, so just one constraint. You set it to 0, but that causes you to have an invariance on the phase space by changing the value of Q3. And then by fixing the value of Q3 to be 0, you have fixed the gauge for the invariance. And that ends up with having 2 degrees of freedom removed. There is a sort of way to convert second class constraints into first class constraints and vice versa, but I will not get into that here. Overall, the distinction is important because these constraints are usually not that easy to convert into each other, and both of them have their difficulties. And it's just practically not very feasible to work with just one or just the other, unless that's exactly what you start from. Now, I said gauge, but what do I mean by gauge, and how can I gauge fix I set something to 0 and then I have gauge invariance? Why do I even know that? So say I have these first class constraints and I weigh them by some parameters, and I apply that via the Poisson bracket to get some infinitesimal change of the function. This is what I will call my infinitesimal transformation. In Maxwell, for example, you can take this as a stand-in for the constraints, and then you can check by taking the Poisson brackets of A and E inside this integral that it actually generates the usual gauge transformations of Maxwell theory. So it changes the vector potential by a gradient. This is the real Gauss constraint. I mean, okay, here there are some sources, here are none, but I mean, doesn't change much. There's a statement in general about this, which needs, of course, some qualifications, but the gist of it is that Noether didn't just prove one theorem, she proved 2 in the same paper, which is surprising to some people because they only really get taught 1, but it's because the second theorem really is something for field theory. The second theorem states that if you have a local symmetry of your theory, for example, in the case of Maxwell theory, it's this. So a theory that acts locally per point, and you can have parameters that vary per point, then those symmetries, via what's called Noether identities, are equivalent to local constraints that act on each point. So the statement for Maxwell theory is that the U1 gauge transformations are dual to the Gauss constraint. And this is a general thing that works in all systems described by Lagrangians. Noether really was goated. God bless her heart. Now the gauge transformation stuff, put all that aside. For second class, you don't really have that general intuition. You don't have anything really. They are just constraints. But as I said, sometimes, okay, I said generically and locally that's true, but it's hard to actually do in practice. You can turn a set of two second-class constraints into a first-class constraint and a gauge fixing. So the example I want to give here is that of the, I think it's called Coulomb gauge. You take the Poisson bracket of these two. So this one you need to set to 0 anyway. And this one is a nice gauge fixing, which a lot of people use. And the Poisson bracket is non-zero in general. So this forms a second-class set of constraints. And if you impose both on the phase space of Maxwell theory, then you change the Poisson structure. But that's not bad, because you have to do it in order to uncover the physical degrees of freedom. Now, there's here comes the reason why I didn't say P right away, but P tilde for the on-shell phase space. The physical phase space is in general different from just imposing those constraints. The physical degrees of freedom are what you get when you take the on-shell phase space and then you fix fix gauges for all of the first-class constraints. So in case of in case of Maxwell theory, you impose the Gauss constraint and then you fix a gauge, and then you have the remaining degrees of freedom. And in principle, you can fix any gauge, literally anything. For second-class constraints, that is not an issue. You just impose them and you have the physical degrees of freedom. Now, here comes the perhaps more physically interesting part. Of course, you start from some kinematical phase space, and there are functions on it which represent stuff that you can possibly talk about as physical quantities. I use observables in quotation marks because this is a semantic warfare that I'm not willing to get my hands bloody in. Instead, I will just focus on certain conditions on functions that are important to keep in mind. The first one is that for first class, you require that the Poisson bracket with the first class stuff weakly vanishes. This is what's called gauge invariance of observables. So the case in Maxwell theory is that if you take the constraint here and you take the Poisson bracket with, for example, the field strength, so the electric field and the magnetic field, then weakly this vanishes. So the electric field strength is an observable. Now, for second class, that's not enough. Second class constraints are annoying in that you have to actually know the stuff that commutes with them in order to know what's observable. Why do we have these restrictions, you can ask? The main point is that what you regard as observables are the functions on the physical phase space. So you need to restrict the set of functions on the whole kinematical phase space in such a way that it corresponds precisely to functions coming from P. And this is precisely those two criteria. It's worth noting that it's also not enough to have this just a weak equality, because you can always make this a weak equality just by redefining the function a little bit. Do you have a question about Noether's second theorem? That the second class condition is relevant for observables. You mean this here? Well, for example, if we take the constraints here, then the physical phase space is very easy to see. It's just the functions of Q1, P1, and Q2, P2. If you have such a function and you want to identify it in the set of the full set of functions on R3, or well, the phase space associated to R3, then it's precisely the functions that commute with the constraints strongly. One and two are equivalent? No. No, not at all. I mean, it's basically any function that you want to call observable needs to satisfy both of these conditions with respect to all constraints that you have. So if you have both first class and second class constraints, a function needs to be both gauge invariant and commute with the second class constraints. Yes, but that's only enough if you only have first class constraints. It requires a stronger condition, but you can think of it as follows. If you have a set of second class constraints, like this one here, then what you're requiring is that the function is gauge invariant, and it also preserves the gauge fixing. Because otherwise it will be a function that doesn't, like it's vector, like the transformations the function generates, or that the gauge fixing generates, take you off of the gauge fixed surface that you started from, that you proposed was your physical phase space. This is one way to see it, for example. And yeah, proxy, it's really like if you have only first class constraints, then this is enough. If you have only second class constraints, then this is enough. But if you have both, then you need both to be true. A function of f, yeah, so some function f. Yes, some polynomial, like the EM field. Can I design a function that does not conserve the gauge fixing condition? I mean, maybe not for f, but maybe for some other function of a, you know? And I mean, I think I can imagine that, because, for example, if you take some function of b, like, for example, just the magnetic field part of it. Actually, no, it has to be the electric field part. But still, I think you can definitely find stuff like that. Aren't all gauge invariant functions reducible to functions of f? I don't know. I don't think looking at a specific case like this is enough to discredit the rule. but really it's just that if you have some function that's gauge invariant in this case, then you will be able to then I think, okay, I mean, in this case, it's a bit difficult, right? Because you only have one constraint in the first place. You only have one constraint, which is the Gauss constraint. So it's first class. And there are no second class constraints. But as soon as you switch to the gauge fixed phase space, where you have imposed the Coulomb gauge, then you need observables to also preserve the gauge fixing. Does that make sense? Now, you can already see it at the bottom. There's now an improved recipe for when you have all of these constraints. The recipe works basically the same way as before, but you apply it to a different Poisson bracket. You apply it to what's called the Dirac bracket, which only matters for when you have second class constraints. So again, remember that second class constraints, when you impose the constraint, you take the Poisson bracket, and then after taking the Poisson bracket, you set the constraints to 0. And then their Poisson bracket is this invertible matrix C here. Because it's invertible, you can call the inverse M here. And then you can define the Dirac bracket on the full kinematical phase space via this formula here, which looks a bit strange, but it's constructed in such a way that it reduces. So it's constructed in such a way so that the Dirac bracket of the second class constraints is exactly 0. And in fact, it's true for all functions, if I remember right. Yeah, so the point is the constraints here in this bracket now commute, at least weakly, and then you can put hats on it, and you don't have any problem. Now, what does this mean for observables? The conditions above can be translated into this Dirac bracket. For the second class part, it's 0 always. So if you just look at any function, and use the Dirac bracket, then this is always 0. So in principle, once you switch to the Dirac bracket for quantization purposes, you can use any function. It's just that the Dirac bracket will change your commutation relations in such a way that if you have something that's not an observable, then it will basically not be contained as an operator in the quantization. For first class stuff, also not much changes, because weakly, the Dirac bracket with the first class constraints is just the Poisson bracket. So if you want, second class constraints are more difficult or more strong because in principle, to identify observables, you have to do more work because you need exactly 0. This is for identifying observables, but this is for any function, by the way. They're also more work because you need to find this Dirac bracket here in order to properly quantize stuff. But first class constraints are also more difficult in that you can never avoid finding out what this, you can never just like remove the constraints from the picture entirely. Whereas when you use the Dirac bracket, you basically remove the second class constraints. This is essentially what it does. You just redefine your Poisson bracket so that the degrees of freedom, which are removed by these second class constraints, so by stuff with gauge fixing, is just removed from the whole set of variables that you had in the first place. Now, how do you even get these constraints? This is probably the most annoying part of the whole procedure. So before we get to that, if you have any questions, let me know now. If not, then I am happy to present to you the world's most chaotic algorithm. Basically, what it does is you start out from some Hamiltonian of your choice on the kinematical starting phase space. For example, you can take the one of Maxwell electromagnetism, which is like E squared plus B squared. And you force it to be an observable. So you force it to satisfy these conditions here. How do you do that? By successively adding constraints so that this holds. How does adding constraints make this easier, you ask? Well, it sometimes does, sometimes doesn't. But it definitely works. So how does it work? So you start from whatever you have in the beginnings, what you call the primary constraints. It can be some first class constraints, some second class constraints. It doesn't matter much. For example, the case for Maxwell theory is that your primary constraint is just setting the conjugate of A0 to vanish. Now, you then do the first step in the algorithm. You take your original Hamiltonian, E squared plus B squared, and you add the constraint with some arbitrary function of the coordinates and momenta. This is okay because in principle, once the constraints vanish, this piece is gone anyway. This is what you could call the gauge Hamiltonian. It's a Hamiltonian that generates time transformations, but it also generates a bit of a gauge transformation with some parameter given by this function here. Now, you do the next step. You ask, okay, is this H0, is this H1 here? Is this, does this commute with my primary constraints? Is this an observable? And if they all weakly vanish, then this is perfectly fine. But in general, on shell of the constraints, you have some stuff left from taking the Poisson bracket. It could be non-zero. And these you just say, okay, I just also make them constraints. Because if they are also constraints, then it weakly vanishes again. Because then I say, okay, I mean, this the Poisson bracket of this is this, but then I say this also vanishes, so it vanishes. It's a bit of a weird trick, but it definitely works. Now, you can add these constraints also back. So you now have the H1 part, and you also add in the secondary constraints, which generate further transformations with further parameters. Now, if, however, there are some of these constraints here where it weakly vanishes, you do something different. Instead of adding something else as a primary constraint, which you can't because there's nothing here, you instead look for the value of this gauge parameter here. You solve because you can expand h1 into h0 and this stuff here, you solve for for the u parameters here. In principle, you will find you won't find a unique solution, but instead you will find some vector space of solutions. And this vector space is precisely parameterized by gauge parameters. This is actually exactly why one interprets these first-class constraints, which often weakly have, where often this is the case here. Where often this is the case. This is why one interprets them as gauge transformations in the first place. And this is also why one says that gauges are redundancies. Because in principle, you do this step, and then you end up with having fixed some of the values of these u here, but you haven't fixed them all. There's still some arbitrary functions of time, which are in here, and which are part of your Hamiltonian, so of your time evolution. So your time evolution is arbitrary up to, and its and the arbitrariness is parameterized by the gauge. So one says that gauge transformations are redundancies, usually at least, precisely because they generate redundancies in the time evolution, indeterminism in the time evolution. And this is also why one needs to gauge fix in order to have time evolution uniquely. Now, one can repeat this procedure again and again and again until it stops. So if all of the u's have been determined, or if all of this is weakly zero. And I mean, if it doesn't, then you have other options. Overall, the result is that you have a final set of constraints and a final total Hamiltonian, which is the original plus some linear combination of these final sets of constraints, and which is an observable in the sense of these criteria here. Some of these ui will be fixed, but some will be arbitrary. And the part that's arbitrary is the true gauge freedom of the system. This is the most systematic criterion by which one can tell what the gauge freedom of a system is. Now, this is basically the end. I'll just give some final comments. This algorithm seems like it's okay. It already looks complicated when you write it down in the most terse form. But in practice, it gets even worse. It gets arbitrarily complicated. It's known that the algorithm, there's no way to tell how long it goes and how often it bifurcates or trifurcates. It can repeat. It can go in loops. It can be very, very, very bad. It's a lot of work. But it's an algorithm, so you know that at some point you will find something that that works. Unless, of course, it doesn't stop. Now, there are many subtleties that I did not get into, some of which are, for example, that sometimes you cannot identify first-class constraints with gauge transformations or redundancies. It's complicated. There are many counterexamples. It's almost as bad as topology, but it's well studied, so you can basically always look something up. What do we get at the end of the algorithm? In the end, you get a new Hamiltonian, basically the stuff here. You get a new Hamiltonian, and you get a new set of constraints, and you know that your Hamiltonian is an observable with respect to those constraints. It's essentially, another way you can take this algorithm is that you ask that all of the constraints you start from are conserved in time. And then you just propagate it from there. Now there's a complete alternative to this whole process. You don't have to do all of the stuff classically and quantize then. You can also just quantize the kinematical phase space directly, which often works if it's something like a vector space. And then you can impose the constraints after quantizing. This is often like something that you do, for example, in BRST, or in its more sophisticated forms like BFV BRST, or BV BFV, or BF squared V, and so forth. But in either case, you basically always need to do some version of this algorithm in order to even know what constraints you have to impose. Are the constraints unique? Ooh, I mean, I feel like the constraint surface is determined uniquely. But so there's no danger of getting inequivalent theories. But in principle, your constraint set is not, the set of constraints doesn't matter as much as the reduced phase, as the physical phase space. So you can have, for example, you can take this algorithm, apply it to Maxwell theory, and get a set of constraints. By my experience, you basically always get the same set of constraints, so it's essentially unique up to my experience with the subject. But you can still take that set of constraints and just rotate them, like take linear combinations and make other constraints from that. And the constraint surface is the same. And then you get the same theory. At least, yeah, it's the zero set of constraints, I would say, is determined by the theory. So it's unique. Yes. Of course, that's not true per se if you follow this quantize first, impose second approach. Then there are probably no statements whatsoever. At least I cannot think of how that would make sense, to have statements that say it's unique. In general, if you have one set of constraints and another set of constraints that give the same surface classically, and you impose them on the quantum side, then I think you get different theories. Conceptually, all of this stuff is, I mean, I say easy in this line here, which is in practice, it's much more difficult, is what I mean to say. For example, the separation into first and second class parts in finding observables and all of this stuff, it's incredibly difficult. It's in fact so difficult that when you look it up for GR in the book that I mentioned in the beginning, you get statements like, okay, we can do this calculation here. The ambitious reader can follow it and will have to fill out like 4 pages between each line. So it's bad, is what I'm trying to say. But the good thing is it's very well studied. So if you are interested in this sort of stuff, even if you don't care about GR so much, there's a very, very nice, very long book by Mark Henno and what's his name, Teitelbaum, about just this quantization stuff. So this is the stop of the section on constraint crash course. Any further questions before we get to the example with which we will stop for today? Okay. If not, then I will get to my final example, which is probably the simplest generally covariant system you can think of, and that is actually interesting and not artificial, which is the worldline action of a particle. So what we will look at is just literally a single particle, just one particle, for example, in Minkowski space. So we have a curve, which we will take to just be this unit interval, and we map it into some manifold with some fixed metric. This is like, okay, I mean, I was gonna say this is like string theory, but one-dimensional, but I feel like it's rather the other way around. So what you have is the dynamical fields are maps from which map some arbitrary parameter time lambda to some point in the manifold. And a key thing for this curve is that at each point you have a tangent vector in the manifold, which is a true vector. Yes, Babs, I can see you. So here, unlike in the rest of the talk, I use my my more favorite convention because I cannot be bothered. Now the action we are using is just that we minimize the length of the curve. So this is what's called the Nambu-Goto action. You just take the tangent vector, the velocity at each point, you take its norm, this is the norm, and you integrate it. So it gives you the length. Now, this is nice, but we will actually use a different action because it's easier to analyze. The Polyakov action is very similar. So we will be working with some, for example, in Minkowski space, where we have global coordinate functions, which we can apply to the curve. And then we get that the curve is represented by the coordinates of the particle. Or we can just do this on a curved spacetime, assume that the curve is contained in some patch, and then we have still coordinate functions. We can give this usual scalar field action in basically this form here. So with derivative of scalar field with some metric stuff. And to distinguish the metric on the world line, so the line of the particle, did not take you as a time as the fourth coordinate. Yes. Man does gravity and it favors mostly minus. It's because I like my time-like stuff positive. So, basically on the world line, we will also have a metric. This metric, of course, is just 1 by 1 because we only have a one-dimensional manifold. So we just put something here, which, I mean, we can just call this n squared, this one component. And the inverse is then just given by 1 over n squared. We will require that this is a density, so similar to the square root of similar to the determinant of metric. Or square root of the determinant, I think. Yeah. So basically, you take the usual scalar field action. So derivative, then you have the metric on the manifold, but the scalar fields are also valued in some internal space with indices mu and nu. And you have some metric on the internal space. And in fact, this metric even depends on the values of the scalar fields. So now you have what's called something like, well, it's a particle. It's a particle moving on a curved spacetime, but this is very similar to stuff that's known from what's called a nonlinear sigma model. This is more like string theory. All right, so there's also the weight of the metric tensor here. for integration over the spacetime manifold. And for good measure, I also included some constant background energy density, which I take to be positive. So in a way, this is a bit like having a cosmological constant if this were like a fully fledged quantum field theory. Now, our full action then is given by taking this and integrating it over d lambda. And it depends on the scalar fields x and on the one component of the metric n. So you have d lambda n, that's already suggestive of what we saw in the ADM action. And then we have the Lagrangian itself. So we can rewrite this again as d lambda times L depending on x, x dot, and n. So again, there's no time derivatives of n here. This should not be here. So let's see. We work with this action here just because it's simpler. In principle, it's known that the Polyakov action here is classically equivalent to this length here. And we will basically just need this to prove the point. Now, as for the equations of motion of this, let's study that in detail. We can vary the action and basically you find some boundary term and you find the actual equations of motion. So the one that comes from varying x, it says that the derivative with respect to lambda time of u, weighted by 1 over n, is 0. So the velocity is constant. When you vary n, you instead get that u squared is given by n times this constant background energy squared. And this is important. This is essentially the on-shell constraint for particles. So p squared equals m squared. Yes, it's still not string theory. Particularly because there's background shit. That wouldn't be conformally invariant. So for fixed endpoints, we now have the equations of motion here, which is basically that the second time derivative is 0. So the particle moves as a straight line in the background. And the second constraint says that the velocity, velocity squared is equal to the speed of light squared. Of course, this should like make you wonder, okay, but this is a constant and lambda is certainly a constant, but n is a field. How is this a constant? And well, it's sort of like, okay, c is a speed, so distance with respect to time, but again, time is an illusion. So the n here translates between quote unquote objective time and the lambda time that we had here. Now, what are solutions of this? We can actually solve this, for example, on Minkowski space. Solutions are easily found as u is given by prefactor n times something linear in lambda. And the square of that needs to be equal to lambda squared. So we find that b needs to be 0. And a squared needs to be equal to lambda squared. And be required to be 0 and to be greater than 0 so that it's future directed. So the velocity is actually constant in lambda time, which tells you in a way that it's a constant of motion with respect to this lambda time. Now, if you want to find x from this, you can write d lambda x is given by n a mu, just by resolving what u is. And this gives you that x is given by some starting position on the manifold times a mu, which gives you the constant velocity, and then you integrate n. Of course, you don't know what n is, but in principle, all you can see is, okay, there's some function of lambda here. So you could, for example, take this as basically equivalent to, x naught plus t over m p naught. So just the usual particle on Minkowski space. You just kind of have to reinterpret this function of lambda here as t. And again, because you can reparameterize time, this is perfectly an option. This would precisely correspond to taking n to be constant in time. So it's definitely a free particle, but what does n really mean? It, just like the lapse we had in the ADM formalism, parameterizes the freedom in the fake coordinate time lambda. So you can do diffeos on the interval just by mapping time to something else, and this will give you a gauge invariance. And now how does this gauge work precisely? So take some diffeo given by a vector field infinitesimally on this real line, on the real line that parameterizes the world line. And you take it to just be the derivative that I give above here. So f of lambda d over d lambda. So what we find is that any infinitesimal diffeo on R is basically given by one function on R. Then the transformation induced by this on all of the fields is the following. The one on the fields x that give the coordinates of the particle is the Lie derivative, and by converting this with the vector field expression, you get that it's just the function scaling the velocity. You can also apply it to the velocity itself. It acts the same way, and then you can rewrite stuff in such a way that you see, okay, luckily enough, it actually just gives the lambda derivative of f times u. So the lambda derivative of this. So the lambda derivative commutes with taking the action of this diffeo. Now what about n? We also say we want it to act like this on n. And the crucial part here is, okay, it's a scalar function, sort of, you would think. It's a function, yes. But it's not really a function. It's a tensor density. And tensor densities, in addition to the usual Lie derivative term, which is just the directional derivative, have an additional term which takes the divergence of the vector field. If you take this into account, you find that also the transformation of n is just the lambda derivative of fn. So all of the transformations really basically work like this. So in addition, mind you, it shows that the gauge invariance we have for reparameterizing this stuff, which we will show is gauge invariance very soon, is actually diffeos. So this is very similar to the ADM stuff. Nah, this is not going to be all of QG. This is the last part for today. Now, let's see that this is actually a symmetry. So this is basically what you could do in GR, but we are going to do this just in this example because it's feasible. So here, you apply the vector field to the action, and you replace all of the instances of the fields such that you get only the changes of the action. You insert all of this. So here's the equations of motion. And here are the vector field changes. And you use in all of this that, okay, 1 over n, you apply quotient rule, blah, 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 and insert that there. And then you expand all of this out. You're free to check the notes. And then you can factor out the pieces in such a way that you see the change of S under this diffeo is precisely given by d lambda, f dl by d lambda, and then df by d lambda times L. Of course, product rule tells you, okay, this is a total derivative. And again, it's of this form, lambda derivative of FL. So the action changes by a total derivative. It's a symmetry. And this is actually exactly the form that you will also find in general relativity. Because it's a symmetry, you get a Noether current, so a conserved quantity. So when you change by a symmetry like this, and your Lagrangian changes by a total derivative k, then your Noether current is given by the derivative by q dot times the change in q minus the boundary term. And you can calculate that for this theory here. And it turns out to be this quantity here. Sadly though, if you remember the equations of motion, this piece here vanishes when the equations of motion hold. It's already recorded, don't worry. And now that we know this is a symmetry, we can proceed with the Hamiltonian analysis and actually verify all of the statements which we made about GR. So, which lambda will you use as a time? In principle, you will have to fix something in order to do time evolution. So we will just fix some, but we will find that there's reparametrization invariance precisely of this kind. So again, we can look for the canonical momenta, this time with respect to lambda time, and find that it's given by the tangent velocity. And we can invert it, just like in GR. Next, we can find that the canonical momentum for n again vanishes, so just like in GR. And it's not invertible, so what do? We do this constraint system stuff, and we use this Lagrangian here, and we provide the Hamiltonian for it. The Hamiltonian, again, is just the naive Hamiltonian that we would use is just this here. And if you check closely, this really is like the constraint on a relativistic particle, this time with the constant lambda. So this constant lambda really takes the role of a mass for the particle. Next, we have the phase space variables. We have x and p, so this is the particle, and we have n and its conjugate, which are something else. And we require that they fulfill canonical commutations. We had this primary constraint that pi is equal to 0, and we require for its conservation. Now we run the Dirac algorithm that the Poisson bracket, which we can evaluate to be this thing here, is also weakly 0. So this gives us our secondary constraint. So now we have done a step and we find, okay, our full new Hamiltonian is h naught minus some phase space, some multiplier k, some parameter, with this stuff here, with this additional stuff. Luckily also, the original naive Hamiltonian we started from is already the secondary constraint that we have to add. So the full Hamiltonian is actually just a sum of those constraints. Yeah, weakly zero means it vanishes when the constraints are zero. Now, again, h and this new secondary constraint directly commute, so there are no further constraints. In principle, then, all we need to do for the phase space analysis is impose those two constraints, and then we can time evolve. We can also quantize it with all of the machinery that we've seen, particularly because we know that the constraint system here is first class. Because you can take, because as we saw, the original Hamiltonian is just a multiple of this constraint. And then the Poisson bracket of those two constraints derived from this here will also be proportional to some constraint. Now, the full Hamiltonian is a sum of constraints, just like in GR. So in physical states, there is no time evolution. Why? Because lambda is unphysical. It's arbitrary time evolution. And we also know what why that is. We have a symmetry of the action, and we know that this leaves the action invariant. We also know the symmetry current for this. The conserved quantity is precisely the constraint that we need to impose. So it's all coming together. So how do we solve this? How do we deal with this, practically speaking? We select a physical time. We take, what we usually does is we take a physical time as the zero component of this vector of these scalar fields x. This is a field, mind you. It's not a gauge, it's not nothing, it's an actual physical field in this theory. With this, we can define these relative derivatives of xi by x naught, and we can convert it into the derivatives with respect to lambda time and get it's just ui by u naught. And then we can also solve the constraints directly and say, okay, u squared is just u naught squared times 1 minus beta squared. And then we can we can solve the constraint either by fixing beta, which we don't want, or by fixing u naught, which makes sense because it's in a way conjugate to x naught. So schematically, when we do this, the EOMs are given by dx by d lambda is u, which is given by the Hamiltonian, x mu, is given by n times p mu. So this is now back in the original like phase space with the extended Hamiltonian we had above. And it's now important what the coefficients here are. The important piece is now this coefficient in the Hamiltonian needs to be the field n, whereas this can be something else. Also, the time derivative of n with respect to lambda time is precisely given by k, which was, well, it's free, it's arbitrary. So overall, we have that time evolution with respect to lambda time, so not with respect to this physical time here, is given by stuff that's determined by n, but the evolution of n is arbitrary. So the time evolution overall is arbitrary. So the latter says that it's completely arbitrary. So now we are going to look at the gauge trafos, just to make this as clear as possible. We have two constraints. They're both first class, so we guess they generate gauge transformations. What was the constraint? The constraints in this case are phi1 given by pi and phi2 given by this. So this is the relativistic mass constraint, and this requires that time evolution of n here is arbitrary. Now, so what does phi1 generate? It generates shifts of n, precisely what it means for pi to be 0. The second one, however, generates shifts of x by p mu times weighted by something. And this, if you look at it and just say like, okay, I mean, well, it's a bit like t, then yeah, this is like time evolution. So what does this do to u? It does nothing. U is in a sense gauge invariant quantity. Now we also had the nota current, which was given by the constraint itself, and this moved the fields by f times u. So if we use this nota current, weighted by coming from the diffeomorphism with vector field from f here, then we can also apply this, and we can say, okay, maybe this is our Hamiltonian. And in fact, yes, if we check the Poisson brackets, it gives us the time derivative. This is, in a sense, precisely what we understand to be the Hamiltonian. But for n, not so much. For n, it commutes, so it's not quite the Hamiltonian. The true Hamiltonian, again, has this piece involving pi and involves the time evolution not just of x, which is encoded in the nota current, and also a piece that encodes the time evolution of this other field n. And this then is perfectly okay. This is compatible if we set that k is actually given by this. So somehow you need to require some conditions on the Hamiltonian to match it with stuff from the symmetry analysis, but overall you can make it so that the canonical side with these constraints generates exactly the motion you would expect from the equations of motion. Now, let's summarize this. We had an action for a free particle which has free motion, which is exactly solvable. But it also has a mass shell constraint. Then we had some time translations or diffeos of the time axis, which are a symmetry of the system. There are some, now there's a Hamiltonian formulation, which has some constraints. For example, the ones that we had here. Now, the Hamiltonian itself is 0 when those constraints hold. So on the physical phase space, the physical degrees of freedom, the ones of the free particle, the time evolution is pure gauge. It's purely arbitrary. So we can specify, for example, n completely by choice, and therefore we also specify a time evolution for x. A choice of n then amounts to also a choice of parametrization. And n, by all means, is basically the same as the lapse function in ADM or in GR. The elapsed time was precisely the integral we saw when solving the equations of motion. So even though the Hamiltonian form is weird, it's perfectly clear, and there's no issue with vanishing Hamiltonians and with arbitrary time evolution. Now we can, for example, choose n to be this function here. This is a sort of field-dependent choice of gauge. We can choose some function g here. And we can then invert for p naught and get it is 1 over g. We get pi is ui over g nu naught and get it's proportional to this beta I that we found in discussing the physical clock. So what we're doing now is we are trying to find a choice of n that relates the lambda time with the physical time. And for this, all we need to find is a specific choice of g. So if we choose, for example, this particular g here, which is a function on phase space, because it depends on the beta, which depend on the x fields. We're very almost done, yes. And then we can find that this g here is actually just the square of the forward velocity, or rather the norm of the forward velocity, divided by u naught. And then we have already solved the constraints. And we also found that this particular choice of n here is what allows us to use the physical time coming from the field x naught as a use of time evolution. When we use this gauge, actually, the form momentum looks precisely like what you would find in a special relativity book. You have some mass here, some Lorentz factor, some component 1, and then the velocity. In this gauge, you have automatically solved the constraints, and we have the time evolution on the worldline, but not from the original Hamiltonian, which was fake time evolution, but true time evolution just by shifting the true clock, the true time coordinate. We can use then that p naught, so the momentum, is precisely what shifts the value of x naught. And in this gauge, at least, then p naught functions as what one calls a relational Hamiltonian. So it's not the Hamiltonian you got from the Legendre transform, but it's the one that actually does generate time evolution. And you can take, for example, p naught expanded at low orders and get, yes, it's the energy, and it involves the true, the usual Hamiltonian. It's the actual energy. So now for the finale, let's just ask, okay, what are the observables in this case? Where is tilde in actual approximation? Where this tilde is in actual, yes, exactly, yeah. Yeah, this is why everyone hates the notation for that. Observables, yes. So phi 1, which was pi, obviously commutes with pi, and it commutes with those other stuff as well. Now, again, these are first class, so all we need is that they weakly commute. But in fact, phi 2 also commutes directly with n, with pi, and with p. So p, which is 0, so it's not so interesting, but also the capital P are Dirac observables. They are strongly Dirac observables. There's not even like a weak equality involved. So as far as weak observables goes, there are no interesting ones. There's a notation and terminology that I didn't introduce so far. Weak observables are the ones where they are observables also like just when you have weak equality, but strong observables are when it's when they commute with all constraints, no matter if first class or not. And there's no weak equalities involved. So overall, what we find is that by choosing a specific gauge for the system, we get back a physical notion of time evolution. For this to work, we needed the time variable x naught. Okay, actually, this is not true. I'm a bit confused now. So what needs to be a Dirac observable? Yeah, this needs to be Hamiltonian. So what we need is that the Dirac observer and that yeah, it's being recorded. Yes. What we need is that the time, it can be basically anything, but it should be conjugate in some sense to something which is a nice Dirac observable and which can function as a Hamiltonian. So in principle then, what we have is we have used of our 4 observables, we have used one as the Hamiltonian, which is P naught, and we use X naught as a clock. So we still have 3 other things left, which we can use as actual observables for which we can do the time evolution. In particular, this piece here, the lambda time evolution, is arbitrary. The X naught evolution is also arbitrary, but the relative evolution of X naught of Xi with respect to X naught is actually physical. And that's precisely what you would expect from the usual formulation of particles moving in flat space-time, where you just have the space coordinates. Now, what we've seen with all of this is that we can take such a system where we know exactly what the physical content is, and we have exactly the same problems as in GR, vanishing Hamiltonian, and coordinate invariance, and no a priori way to know what to interpret as physical time evolution. And we can actually understand it. It's perfectly reasonable. We have the technology to quantize all of this, and we have a method of understanding what actually counts as an observable. And we know also what criteria to apply so that we find a physical clock and a physical time evolution with respect, which is not the coordinate time, but some physical time. The problem in GR is that it's hard to find actual observables. It's hard to find a good clock. It's hard to find a good Hamiltonian for that clock. But in principle, if you can find those, then all of the stuff we did so far in this long example here, with symmetries, with Hamiltonian analysis, with gauge fixing, and with relational observables, all of this works in GR, and then you can apply quantization and arrive at basically quantum gravity. That's it. That's all for today. I will now take questions after a short water break. And yes, I'm happy to discuss. I'm hydrating. Okay. Prox asks, I wanted to come back to the issue of having two constraint conditions in defining the observables. For first class, you have gauge invariance. For second class, you have strange commutativity. Why would you take the reduced phase space and consider functions only on it? Why the second one? Why it's not necessarily trivial? I can repeat the example from the beginning. So the case in point was you have some particle on R3 and you restrain it to be on just where the z equals 0 plane. And when you do that, you don't have the observables Q3 and P3 anymore. So they are not part of your physical phase space once you properly reduce. Yes. Now, the second condition that I listed is one that selects functions which take which you can reconstruct directly from functions only on the reduced phase space. So in another example, it would be that you, so take for example a particle and you restrain it onto a sphere. The particle has 3 coordinates. Yeah, you have some function fq1, q2, q3, p1, p2, p3. Yes. Well, no. No. You cannot apply. You cannot. The criterion 1 doesn't apply because q3 and p3 together are second class. So this is a second class constraint example. If you want an example where you have first class and second class constraints, then you could say my constraints are P2 equal to 0 and Q3 and P3 equal to 0. Then you would have to apply both criteria at the same time. Then your set of observables would be functions of Q1, Q2, P1, P2, which are also constant in Q2. So in this trivial case, of course, it means that you just remove the dependence of Q2. But in more involved examples, it's different. Like in the case of, say, Maxwell theory or something, then it would be different. Like in Maxwell theory, for example, it would mean if you, yes. So really, it depends on what your set of constraints is. In Maxwell theory, you only have one first class constraint. And then you say, okay, I take my observables are anything that's gauge invariant. That's really it. Or rather, anything that's weakly gauge invariant. So something that when the constraints hold is gauge invariant. I mean, not really, because in general, if you just have some second-class constraints, they don't generate a gauge invariance. Like they generate some transformation on the fields, but it's not gauge invariance. It's not going to be gauge invariance. It's just a shift. It's just a shift in, like, if you just shift Q3 to Q3 plus A, then it's just a shift of the value. What makes one a gauge or not is precisely the question of this non-unique solutions here. Gauge, or rather redundancy, is that you have indeterminate time evolution. You can only call something like gauge invariance or redundant transformations if it's one of those, if it generates something like that. Otherwise, it's literally just some random transformation. And in principle, second-class constraints can be absolutely anything. Yes, but it's also, I think, the only meaningful sense of the word gauge invariance, I think. Like, I think you can either, like, the only meaningful way you can use these words is gauge invariance is something where you have, like, gauge potentials that transform with, like, some derivative stuff. And redundant transformations are where you have indeterminate time evolution. Anything else is pretty much semantics, I think. Yes. So then what role are the second class ones? I mean, if you have them, you have them. Otherwise, you don't, really. Heuristically, what they do is they remove one canonical pair each. Like, each pair removes one canonical pair. They don't do anything, really. They don't have any geometrical meaning, in a sense. It's just that you remove two coordinates from your phase space. What's the impetus? I mean, again, you can ask, how do you get constraints? You run the Dirac algorithm and you get them. And often you just get them. There's also cases, of course, where you have some system and you impose some constraints by hand because you want to. But they just pop up, basically. Like, all constraints are a redundancy in the sense that only once you solve the constraints do you actually get physical degrees of freedom. Right? You need to impose all of these constraints coming from the Dirac algorithm so that you get the initial data of a system that you can actually time evolve. The second class, so if you want well-postness, okay. So as far as well-postness of the theory of the initial value problem goes, this is precisely where the Dirac algorithm comes in. You have some theory, you have some stuff for the kinematic of phase space, and you ask, is the time evolution well-defined? Then, okay, you can take the naive Hamiltonian and run it on that, but that's not the theory that you started from. Because the theory that you started from has these primary constraints. And then, well-postness of the theory implies that you run the Dirac algorithm, you get the full set of constraints, and you impose the full set of constraints. And this full set will in general have both first class and second class stuff. And all of these need to hold so that the theory is well posed. In addition to that, for every first class constraint, you have a redundancy, a gauge invariance. And you need to fix those gauges to have unique time evolution. So, okay. So I guess the crux of my question is the nature of the obstruction to well-posedness coming from the second-class constraints. I mean, in principle, think of the particle that you restrict to a plane. How are you going to do that? You apply some force, some potential. And then, is it well-posed if you have the additional degrees of freedom there? Yes, but that's not the question of what is an observable of the system. The reduced phase space is definitely the one where you just have the degrees of freedom of the particle that has already been constrained. The particle that has already been constrained does not have movement in the z direction. I mean, you don't have to put it in by hand. Again, you can just get second class constraints coming from that algorithm. Okay, so right, okay, but you have to put it in by hand, or I guess a particle on a plane example. As you said, it's well posed while keeping the third coordinate. Yes, but so it seems like external input where that determines whether or not you keep those DOF, not this algorithm. I mean, this is an example where you impose it by hand. You can also just impose it by hand. If you impose constraints by hand, then you have to know what those constraints mean, basically. Okay, I mean, prox, we can talk about this in more detail after the seminar. Okay, I see one more question. No? No more question? Okay. Yeah. So, with regards to the overall structure of this mini series, there's a couple more things here. So, seeing as this one today took a bit of time, probably next time we're gonna just do 2 of those. And then another one will be with another 2, maybe. And then hopefully there will be time for a last session of just Outlook and just Q&A and just discussion. So either way, I think, yeah, this is like a general picture of the stuff that happens in quantizing GR. Next time, I hope to get more concrete with the GR side of things. And yes, I hope you stick around.